So this is the fourth in a series of videos on two problems. The third video you might have skipped if you knew how to read a standard normal table. And what we're doing here is we're looking at two problems and seeing how they're related and how they're different. The first one was that the first question we answered was pick a student at random and the probability that they're greater than 6.1. Remember, this is the original problem. You're at a college. The average height is 68 inches and the average standard deviation is 3. The standard deviation is 3 inches, and we're assuming a normal distribution. So you choose a student at random was probability they're greater than 6'1". And we found that that probability is 4.8%. And what I would like you to see and both understand intuitively and mechanically that the second question, that you walk into a random class, and if there are 37 students in that random class, what's the probability that the average height is 6.1? And what we're getting at here, the intuition here, is that the probability of a single extraordinary event, that is someone's very tall, is much greater than the probability that on average you have an extraordinary event. And that's in some sense at the heart of what we do in statistics, so it's important to pay attention to that. So let's look at the second problem. Well, the key to the second problem is we have what's called the sampling distribution of an estimator, and in this case of the sample mean that we're going to call x bar. And the key here is that x bar is both a number for a single sample, but you could imagine taking lots and lots of different samples. So you can imagine that day after day, university after university, you went into lots of classes of 37 students, and for each one of them you came up with the average height, and you would get a sampling distribution of the sample mean. And the key is that x bar, under certain conditions, will be normally distributed with a mean equal to mu and a standard deviation equal to sigma over the square root of n. Now, what assumptions do we need to make here? We need to make the assumption that the original random variable is distributed with a sample mean of mu and a standard deviation of sigma. And the key points here is that the sample mean is unbiased, an unbiased estimator, and it has a much smaller and well-defined variance or standard deviation. And that's what we see here. So in this case, let's think about how to plug these numbers in. So what we have here is the mean is 68 inches, so that's the same. So we have x bar is distributed normally with a mean of 68 inches. And a standard deviation of 3 inches over the square root of 37. And that's, let's just plug that into our calculator and see what we get. So be careful here. What I would do is I go 3 divided by, I would go 3 divided by parentheses, and then I would go 37 raised to the 0.5. That's the way I do square roots. And that's 0.49 roughly. So x bar is normally distributed with mean of 68 inches, standard deviation of 0.49. And this is the problem here that we're going to do translate into a z, and when we translate z, use the standard normal distribution. So what we want to do is if x bar, let's write this down again, x bar is normally distributed, mean of 68 inches, standard deviation of 0.49 inches, and we want to find the probability that x bar is greater than, let's see, it's 6'1". Let's see, 6 foot 1 inch, 6 times 12, 72, 73 inches. And we're going to translate this x bar into a z, and the way we do this into a z is we want to do let's see, zi is equal to xi minus mu over sigma, but be careful here. The sigma here, since this is x bar, is not going to be our original sigma, but the sigma for our sample mean, right? So some books will actually write it out like this. Zi is equal to xi minus sigma, mu sigma over square root of n. It doesn't matter which notation you use. The key is which number you use. And the key number we're going to use is not the 3 inches, but the 3 inches divided by the square root of 37, so the 0.49. That's the key. So whichever one makes more sense to you, then we're going to have 73 minus 68 over 0.49. Let's just plug that into our calculator and see what we get. So we get 73 minus 68 divided by 0.49. You get 10.2. In other words, the probability that you get the average height greater than 6'1" is equivalent to getting a mean that's 10 standard deviations greater than the average. So let's look at our z-table. Well, if we look at our z-table, what we quickly see is our z-table only goes 3.9, and that's 0.999997. So essentially this is close to impossible, and this is going to be approximately 0. Let's say it's approximately 0.01%. So let's look at go back to our original problem. What we saw is that if you pick a student at random, then the probability that they're taller than 6'1" is about 5%. But if you look at question number 2, that is, what's probably you walk into a class and there's 37 students, and the average height of all 37 students is greater than 6.1, that's going to be less than 0.1%. And that kind of matches our intuition. We might be surprised at how different they are, but the key to understanding a lot of what we're going to do in what you're going to do in statistics, both in this class and future classes, is understanding the distinction between these two problems.